Hello? Oh, okay. Okay, so is it working now? Okay, cool. That's really strange. All right. Terms of announcements, deadlines that are coming up. I am hopeful that I will be able to release the remaining midterm exam tomorrow at 5 o'clock. As you may suspect from the activity on Piazza about the exam number 3, there are a lot of meetings that I am having as a result of that. And so I am a little bit behind on getting that exam written. I have probably about half of it written, and I'm hopeful that in between meetings I will be able to get the rest of it done and get it out to you guys. The small group activity number 5, which is the last of them, is due tomorrow at 5 as well. The quiz associated with it will open at that point and will be due on Friday at 5, which is the same time that the 2 remaining homework assignments, which are relatively short, will be due as well. Those are homeworks 13 and 14, if I'm remembering correctly. The 3 parts of the final exam will open on Monday in the morning, and those 3 parts, as well as the 4th midterm, will be due at the end of finals week, Friday at 5. Trying to remember what else. Oh, yes. So extended office hours. I am planning to have extended office hours certainly Friday and Saturday of this week. I do not have the specific times for that yet. I will definitely have extended office hours Thursday and Friday of next week for most of the day. I will have some extended office hours Monday, Tuesday, and Wednesday, but they may not be as extensive as Thursday and Friday. Again, I do not have the specific times for those yet either. Does anybody have any logistical questions before we get on to the content for today? I do have the chat window up, so I'll be following along on questions as they come up. All right, I will start getting into some content. So let me share screen. And we will see what we can do. All right, so I'm going to come back up here. Okay, so we had just gone through redox reactions on Monday and Tuesday, and we went over electrochemistry from the initially talking about very briefly the different kinds of cells that are possible. We then went through galvanic cells in some detail, where we developed the concepts of half reactions at on each side. Let me actually back up and I will show the slides we did on that as sort of a reminder. So we talked about the anode half cell, the cathode half cell, the flow of electrons from anode to cathode, the flow of ions to complete the circuit through the salt bridge. We talked about cell notation, and we talked about the voltage being a function of the 2 half reactions. We talked about inert electrodes. We talked about the standard reduction potentials, which are measured against the standard hydrogen electrode. Excuse me. We talked about how to determine those standard reduction potentials, that the standard cell potential is the cathode cell potential minus the cathode reduction potential minus the anode reduction potential. And that is despite the fact that at the anode oxidation is happening rather than reduction. That's why there's a minus sign here. We can look up the standard reduction potentials, which are measured against the standard reduction potential of the hydrogen electrode. And then we talked about how to relate three main quantities: the standard cell potential, the delta G under standard conditions for the reaction, and the equilibrium constant. This triangle was in the textbook. And then we talked about how to relate the delta G for the reaction under whatever conditions we have as determined by the reaction quotient Q to the standard delta G. And then using that expression which we had before from last week's material, we plug in the expressions for the work, which is minus n the number of moles of electrons that are part of the balanced redox equation, Faraday's constant F, and the cell potential. We were able to plug that in both for delta G and delta G standard in order to find a way to determine the voltage across the cell under any conditions we want using Q. And so that is where we ended on Monday and Tuesday. Monday and Tuesday we're covering the same material. And so today we are going to go through interpreting some of that information in light of specific types of cells, starting with the galvanic cells and then moving on to some others. What you see here is a diagram showing the first main types of batteries that were sold. This particular type of battery is not used very commonly anymore, but it was one of the initial types of batteries that was sold before the standard type of sort of, you know, Duracell or Eveready batteries that are out now. We'll get to what those are in a moment. So we have a metal cover, we have a metal bottom cover, and those serve as connecting to the two electrodes. So one electrode is made up of the zinc can itself. There's a porous separator which allows the, which basically acts as a salt bridge. And we have manganese oxide, we have zinc chloride, we have ammonium chloride and water that here in a paste. And then a carbon rod that's acting as the other electrode, which passes through an insulating seal to the top. And so what we have going on in this is that we have the manganese oxide, MnO2, converting to Mn2O3. So you should be able to tell that there's an oxidation number change as a result of that. And then we have zinc that is converting from the zinc solid to the zinc 2+ ion here. So you have an oxidation number going the other direction related to this. And so the paste that we have here is acting as the medium through which the ions diffuse. The ions can diffuse to the zinc can, and the zinc can itself is ends up dissolving away to make the zinc 2+ into the paste. So, but this one, we're not going to spend too much time on this one because this one has been supplanted by alkaline batteries, which you've probably heard described before. So these are what are typically used now for commercial batteries that you buy. As the name suggests, this happens under basic conditions. And so you'll notice here that we have the reaction written, but it's not a balanced, well, let's see, is it 2, 4? Yeah, actually that is a balanced reaction, excuse me. And so we have the zinc changing oxidation state, we have the manganese changing oxidation state as well. So you have the bottom metal cover, which is electrically connected to the anode current collector, which is a little spike that goes into the zinc powder that we have in here, and with potassium hydroxide as the anode. We have a porous separator, which acts as our salt bridge. And then we have on the outside the MnO2 powder mixed with coal dust to be the cathode. And then that is in electrical contact with the metal top cover. Okay, so then you've probably also heard of NiCad batteries, or nickel cadmium batteries. So we have similar kinds of arrangements where we have a metal top cover, insulating ring, an electrode collector on one side, an electrode collector on the other. But one of the things that they do in this case is that they will make the layers of the separator, the negative electrode, and then the positive electrode. And then they take those layers and sort of like a cinnamon roll, they call it here a jelly roll. They start at one end and then they just roll it up. And so they very carefully ensure that, you see, the purple layers here are shorter than the, well, I guess we have two different shades of purple. You'll have to pardon me, I'm slightly colorblind. So we have a darkish purple here, and I guess we have a lightish purple here. And the lightish purple ones are in contact up here. The darkish purple ones are connected down here. And so the benefit of doing this kind of arrangement is that you now have a lot of surface area. And as you might imagine, one of the limiting factors into how quickly a battery can discharge its reaction is based upon the surface area of the salt bridge. And so our salt bridge then, in this kind of case, is extremely huge as it goes through each roll of this jelly roll arrangement. And so we tend to find that this kind of arrangement of batteries that is commonly used in the nickel cadmium batteries can discharge its energy much more rapidly. And as a result of that, it can bear its voltage under a much more heavy load. Okay, so those are three examples of galvanic cells. So the sort of standard dry cell batteries, the alkaline batteries, and the nickel cadmium batteries. There are several more types over and above this. So there are wet cells, for example, which are used in car batteries. Some of these are rechargeable, some of them are not. So there are a bunch of these different kinds, but this gives you sort of a flavor of the types that are available. The next type of cell we're going to talk about is a concentration cell. And the idea of a concentration cell is that you have the same reaction happening at the anode and the cathode, just in reverse. So at the anode, in this particular example, we have nickel going to nickel 2+ and giving off 2 electrons. So essentially this anode is dissolving into the solution, and the electrons from the nickel are crossing here to the cathode, where exactly the reverse reaction is happening, where nickel 2+ from the solution is depositing onto the surface, grabbing the electrons to make nickel solid. And then you have a salt bridge that completes the circuit here. But if it's the same reaction, just in reverse, why does the reaction happen? Well, it happens because you have different concentrations in the solution. In this case, you have a very, very low concentration of the nickel 2+ to begin with, and you have a very high concentration of the nickel 2+ here. And so as a result, what happens is that the nickel 2+ will deposit, bringing this concentration down. The nickel 2+ will be increasing on this side as the nickel dissolves into the solution, and it will discharge until you end up with equal concentrations on the two sides. And so once you have equal concentrations, then there is no voltage that is provided across the two electrodes. And so this picture is a little bit misleading, and the reason it's misleading is that I think what happened was that whoever made this picture took a different picture and then sort of relabeled it. But this electrode which is made of nickel, is a different color from this electrode, which is also made of nickel. So I think they brought one where they had one electrode here that's a silvery metal, and then this one might have been copper or something, but they just relabeled it nickel. So that's misleading. The second thing that's misleading is that if you look at the concentrations that you have, this one looks more concentrated than this one does, but over here they should be the same concentration, so the colors should have changed in this picture as well. So please just be aware of some of the misleading aspects of the diagram and focus on the aspects that are actually relevant here. We have the same electrode, which is labeled correctly. We have oxidation happening at the anode, reduction happening at the cathode, but they are the same reaction in reverse. And the reaction continues until you have equal concentrations on the two halves, in the two half cells. And so you notice here that we have a voltage. That voltage that we get is a result of the reaction quotient in the overall reaction. And as the reaction discharges, as the cell discharges, this concentration goes up, this concentration goes down until gradually the voltage becomes zero when the concentrations are equal to each other. Okay. The next type of cell that we want to mention is what's known as a fuel cell. And so when I first introduced this idea very briefly on Monday and Tuesday, I introduced it as talking about there being a reaction that's happening, basically wanting to counteract this concept of the concentrations changing as the reaction proceeds, because as you can tell, the voltage changes as the concentrations change. And so for a battery, you would really like to maintain a constant voltage. And so what is often done is to generate something called a fuel cell, where what you're doing is you're feeding in a feedstock, and you're feeding in another feedstock on this side. And so the reaction that's happening in this particular fuel cell is just like the burning of burning of hydrogen to form water. And so we bring the hydrogen in on one side, we bring the oxygen in on the other side. They diffuse through into the anode and into the cathode. We have an electrolyte here that acts as the salt bridge. And electrons transfer across, and what happens on this side then is that the electrons join with the O2 minus that gets formed. The hydrogen joins it to make water, and the water leaves. And so you're pumping in oxygen, you're pumping in hydrogen, you're pumping out water, and you get electrical power as a result of this. So even though the reaction is chemically written the same way as just combustion, because we are separating the loss of electrons from hydrogen and the gaining of electrons by oxygen, we are able to harness that electrical power and use it for to drive electrical work that's happening. And so, so this is an electrochemical redox reaction rather than a combustion redox reaction in this particular case. This can also be done with other types of fuels. Very often methanol is another example that would be used. And the setup would be exactly the same way. And one of the advantages of doing it this particular way is that as long as you keep a constant pressure of the hydrogen or of the methanol that you're flowing through as it goes along, you just can turn on and off the battery by whether or not you are flowing your feedstocks. And you have a constant voltage that's being applied when you have constant pressures that you're applying, because it's a flow system and you're not ending up, you have a steady state pressure that's being applied. So that's the idea of a fuel cell. And so let me mention as well, where do we tend to see fuel cells being used? Well, one place is that there have been proposals for automobile engines that use this instead. And so you would have a tank of oxygen, you'd have a tank of hydrogen or a tank of methanol or something like this that would then flow through this kind of system and would, and you harness the electrical power to drive the electrical motors on the car rather than using an internal combustion engine. And one of the reasons for this is that an electrochemical cell like this is more efficient in terms of getting the fraction of the energy out of it and turning it into power, is more efficient than an internal combustion engine is. And so as a result, you'll have a much more efficient automobile at that point. However, you have to combine that with hazard assessment. And a hazard assessment you have to deal with is you have a pressurized container of oxygen, you have a pressurized container of a fuel, and you get into an automobile accident, boom, you have a problem. So, so the hazards have to be evaluated in conjunction with the energy saving benefits that you get from using it. And there's sort of a balancing act that goes into figuring out what's which is a better approach to be using. Okay, now I mentioned as well that corrosion is a galvanic process. And so let's talk a little bit about that idea. The idea here is that if you have some iron and you have a droplet of water that can form just through rain or humidity, where you have dew that forms on a surface, and if you have oxygen that comes in at the cathodic site, then it forms water, and so you are then excuse me, gaining electrons as this process happens. And then over here, you have iron 2+ that's formed as the electrons transfer the other direction, and the iron 2+ joins with oxygen to form rust that's formed on the surface as well. And in this particular case, when it deposits, you end up with sort of etching away of the iron underneath and depositing in adjacent locations sort of a rough surface of this iron oxide that's formed. Now, in some cases, so aluminum is a good example of this instead of iron, aluminum forms a nice even layer of aluminum oxide. And so you don't, what you end up with in this case is something called passivation, where the surface ends up becoming aluminum oxide, and that prevents access of atmospheric oxygen to the interior of the aluminum. And so aluminum is self-passivating, and so you don't end up with major corrosion that ends up happening on aluminum. But in iron, because of how the reaction works, you end up with the deposition of the iron oxide away from the location very slightly, where the iron's getting etched away. And so iron does not self-passivate very well, and it will corrode away. So if you need to have an iron component that is in environmental conditions, how do you prevent the problem? Well, one way is to paint it. Now, unfortunately, paint can get scraped off, and then you get rust at those points where the paint scrapes off. You can make an alloy. So stainless steel has some chromium that's added into it, and chromium will passivate the surface of the iron. And so you end up with a chromium oxide layer that then coats uniformly the surface of the iron chromium alloy, and as a result, that prevents continued corrosion of the iron. You can plate it. So we're going to talk in a moment about electrolytic cells, which let you deposit a metal onto the surface of another metal. And so you could zinc coat iron, which is known as galvanized iron or galvanized steel. And zinc has a lower reduction potential than iron, so it ends up oxidizing before the iron does. And so that ends up preventing the iron from getting corroded away. Or in some cases, you can use what's known as a sacrificial anode. And so the idea is if you have an object you're trying to protect down here, you have an anode that's made of another material that, that oxidizes more easily than this object does. Maybe you make it out of zinc and you just run a wire from the object you're protecting to the zinc, and you put it close enough that you can have a current of ions that are flowing towards the object you're trying to protect, and that ends up, as a result, this will then start to etch away while this does not, and it ends up getting protected. So there are a bunch of different strategies that can be used using an understanding of electrochemistry to protect a component that you don't want to corrode. All right. Finally, we're going to talk about electrolysis, which is essentially the inverse of a galvanic cell. So remember that in a galvanic cell, what we did was we found a redox reaction that is spontaneous. So it has a negative delta G under the conditions that we're looking at. Another way to put that is that it has a positive E cell. Cell voltage that would be applied. That means that the redox reaction we're talking about is spontaneous. So if we looked at an example where we look at the half reaction for Cl minus going to Cl2 and Na plus going to Na, this is running against spontaneity. So so if we took sodium metal and chlorine gas and mixed them, spontaneously they would form sodium chloride salt. But if we separate the reactions and then we have, so that we have an anode and a cathode, and we have a molten sodium chloride, so we have to go to really high temperatures to make that happen, a porous screen in between, and then we apply a voltage source in between so that we are essentially using an outside battery or electrical generator or something of that sort to drive the reaction the other direction, then we can make the reactions go backwards. And so in this case, what happens is that the molten sodium chloride salt, we will have two chloride ions coming together to form chlorine gas, which can be bubbled away and then collected. And then those two electrons are produced that go to our external voltage source. And then electrons are given by that external voltage source to our sodium side, where two sodium ions come together with those electrons to form sodium metal, which can then be collected. So if we look at what those two reduction potentials are, I'm going to back up and see if those happen to be in our table that we had earlier. I didn't actually check this beforehand. Let's see. So sodium here, we have a voltage of minus 2.71. And the chlorine we have up here of 1.36. And so if we have a cell voltage between those two under standard conditions of, let's see, 1.36, 2.71, so that would be 4.07 volts. So if we would have to apply a backwards voltage of more than 5.07 volts in order to drive this reaction backwards to form chlorine and gas and sodium metal. But there aren't many other ways to make sodium metal. And so this is actually almost as efficient as we can get in doing that. So this kind of reaction would be done in order to generate sodium metal. Another example of this, which I think is an example you might have done in your Chem 111 or Chem 112 lab, is the electrolysis of water. And it's also the focus of one of the a part of the small group activity number 5 that we're dealing with. So we have a voltage source, we have an anode and a cathode, and we have water that we've added sulfuric acid to primarily to serve as an electrolyte so that we can have a conduction of electricity across here. And at the anode, we have oxygen bubbling up, and at the cathode, we have hydrogen gas bubbling up. And so this is a particularly good way to generate hydrogen gas. All right. We can also use, as I mentioned, we can also use an electrolytic cell to electroplate materials. So in this particular case, we have a solution of silver, silver nitrate. We have a silver anode, and we have a voltage source where by driving this reaction, we are pulling electrons away from the silver anode and forming more silver plus ions. And then at the cathode, those electrons are then grabbing silver ions from solution and forming a silver plate on the surface of the spoon, which is some other metal that we put into solution. And we have now silver plated our silverware, or you could silver plate jewelry this way. And so again, this is the opposite direction of what we would expect spontaneously to happen. So we use an external voltage source to drive the reaction backwards in order to put the metal plating onto whatever silverware we were using. So this is used to silver plate things. You can gold plate things by this method as well. You can galvanize steel, which we talked about earlier, to prevent corrosion by plating zinc onto the surface of iron. Most kinds of metals you can then plate onto a surface by this kind of mechanism. So in particular, for metal plating and for doing the stoichiometry of a reaction, say you're using the reaction to make sodium metal, for example, you can do some quantitative analysis of this to find out how much of the material you're going to make. So what you do here is you have your charge that you are using to apply to the system. The charge, if you use Faraday's constant here, tells you how many moles of electrons you're using. And so if you have 1 mole of electrons, then that would be 1 mole of silver that you end up depositing, for example, because it's a silver plus 1 going to silver neutral. So 1 mole of electrons will make 1 mole of silver. If you're doing maybe a copper plating, where you're starting with copper in its +2 oxidation state, then you would need 2 moles of electrons for every 1 mole of copper that you are putting on. And then you can compare that to some electrical values here. If you have a known current that you are using, which remember is going to relate coulombs per second that are going along the wire. And then you multiply that by how long you do the electroplating, and that gives you the charge as well. So you can relate the electrical components, the current times the time, to get the amount of charge, which is the number of moles of charge times Faraday's constant. And so you can do stoichiometry in this kind of system relatively easily as a result. Okay. So that's it on going through sort of the bestiary of different types of electrochemical cells. We have that's the last of the new material for this week. And I know that this was kind of a fire hose of information today, and it was a fire hose of information on Monday and Tuesday as well. So I'm happy to open this up to questions. I also have a bunch of muddiest points that I've pulled off of Piazza that I can start going through. In terms of the muddiest points from Piazza, there were quite a few that were relating to the small group activity. and I'm happy to go over some of those. And then there are quite a few muddiest points dealing with the redox stuff and the electrochemistry stuff. But why don't I first open this up to whether there are any questions over what I just went over before I go to the muddiest points. So I'm going to stop sharing screen for a minute. I will also change the settings so people can unmute themselves if you have a question, or you can type it into the chat. If I don't get specific questions, I will reshare screen and start going through the muddiest points. All right, not seeing questions, so I will reshare screen. And let's start talking about some of the muddiest points. All right, so some things on the group activity. So what I'm going to do, I'm going to put this over to the side, get rid of that so that we can see the questions. And I'm going to look through some of the guided inquiry activity questions that we're dealing with. So first question I had, how do you know when a reaction is endothermic or exothermic? So that's related to question 3 here. So in question 1, you should have written the reaction for the electrolysis of liquid water, which incidentally was just a couple of slides back in what we just went through. And then in question 2, you determined the standard enthalpy change for the reaction you wrote in question 1. So how do you know when a reaction is endothermic or exothermic? Does somebody in the chat know how to answer that question if you know the standard enthalpy change for the reaction? I think the first thing I'm going to ask is, okay, so Olivia says, I believe it depends on whether your delta H is positive or negative. Right. So question 2 talks about the standard enthalpy change that is in fact delta H. Well, if delta H is positive, then that means that the system ends up at a higher energy than it started at, meaning it has absorbed energy from the environment in order to do that. And so that is endothermic. If delta H is negative, that means that the enthalpy ends up at a lower position than it started at, meaning that it has released energy to the environment, making it exothermic. So question 3 is just saying, look at question 2, is it positive or negative? Does that mean it's endothermic or exothermic? Okay. Question 5, there was some confusion about the wording. Why does your answer to question 4 have the sign that it does? Give at least 2 contributing reasons. So in question 4, you calculated the standard entropy change for the reaction you wrote in question 1. So the wording here is, your answer to question 4 is either going to be positive or it's going to be negative. And so what I'm asking in question 5 is, if it's positive, why is it positive? If it's negative, why is it negative? That's all that is asking. So, and entropy, remember, is a measure of the disorder of the system. So you should have at least 2 contributing reasons that are part of this answer that explain why the entropy goes up or why the entropy goes down. That's the idea. Okay, question 6. If delta S and delta H, okay, if delta H and delta S for the reaction you wrote in question 1 are independent of temperature, under what conditions will this reaction be spontaneous? And someone on Piazza was confused because, well, the only thing we talked about that has to do with spontaneity is temperature. So what else could we talk about? So what is the relationship among delta H, delta S, and temperature? Does somebody remember that relationship? I'm sorry, excuse me. Delta H, delta S, and spontaneity. Does anybody remember that relationship? While somebody is trying to type in an answer to that, I am going to make a copy of this so that I can type in some answers to it, and it's not going to automatically go into everybody's version of the file. Get back down here. So what's the relationship? Isn't there a graph that relates delta H and delta S with free energy and temperature? There is a way to graph it, absolutely. But we have something that has to do with delta H. So I'm going to put some space in here. We have something that has to do with delta S. And there's something that has to do with temperature. And there's something that has to do with delta G. What is the equation that relates these? So Brooke has put it into the chat correctly. So delta G equals delta H minus T delta S. Usually the T comes before there. Right. And we also know that the criterion for spontaneity is delta G less than or equal to 0. Right. So the question here is saying that this is independent of temperature, this is independent of temperature, but delta G is not independent of temperature. So this equation here tells you the temperature dependence of delta G. So I'm going to take this, put it down here, and say, and what we do now is we say, we've calculated delta H back in question 2. We calculated delta S in question 4. You put them into this expression, and you figure out under what conditions for what temperatures T is it less than 0. All right. Question 7. Actually, notice that several of these, how do you get started? How do you get started? So a lot of these are just, how do you interpret this question? So in an electrochemical cell, a non-spontaneous reaction can be forced to occur by applying an external voltage. In doing so, the energy input into the system is input into the system via an electrical current. Specifically, the electrolysis of water requires this much electrical energy and this much heat energy to maintain it. So how much total energy is required to put into the system for the reaction you wrote in question 1? Well, don't overthink this. You're told it takes this much energy per mole of water and this much heat per mole of water. Add them together. Then compare that to your reaction in question 1 and see, do I have 1 mole of water or do I have some other moles of water up there? That's it. Don't overthink it. Question 9, how do we get started? Write the chemical reaction for the combustion of gaseous hydrogen and oxygen in the atmosphere. Okay, what I'm going to do is I'm going to pick a different molecule and talk about how to get started. Let's talk about methane. I'm going to insert equation, CH, let's see here, I want to do CH4 gas. Combustion, remember, is in an oxygen atmosphere. And so when we have a combustion reaction, what does carbon turn into when we have a combustion reaction? Somebody in the chat tell me, please. CO2, correct. So CO2. And what does hydrogen turn into when it combusts? Water. H2O. Although in this The physical state that is appropriate for 298 Kelvin is the liquid. Now, we balance the reaction. So we have one carbon, we have one carbon. We have 4 hydrogens, we need 4 hydrogens. We have 1, 2, 3, 4 oxygens, so we need 2 oxygen molecules. We're done. So now just follow this same procedure for hydrogen gas instead of for methane. Okay. 16, when temperature was added, I got a, whoops, sorry, when temperature was added, I got a really large number, is that right? 16. At 298 Kelvin, how much work can be done by 1 mole of the combustion of hydrogen gas under standard conditions? And so this is following a section that relates the amount of work that can be done to the Gibbs free energy. So presumably this has to do with calculating delta G at 298 Kelvin. And for that, we need the same equation that we had here. I'm going to bring that down. And so you know the delta H, you know the delta S, you plug in the temperature and you get delta G. Now, when you get a very large number here, what I would suggest that you do is make very certain that you're paying attention to units. What units do we normally use for delta H? No, it's often kilojoules per mole. What units do we use for entropy? Usually that is joules per mole Kelvin. Notice that this is in kilojoules, but this is in joules. So if you're going to combine them in this way, you have to get them into the same units. So usually what happens is that when you take something that's joules per mole Kelvin, multiply it by a temperature in Kelvin, you get a large number because you got a lot of joules. So you probably want to convert joules into kilojoules in this case. So that's what I would suggest is probably going on. Question 17. To create 1 mole of hydrogen gas that you used in question 16, water had to be split by electrolysis. How much energy did that take? And someone on Piazza asked me, I don't know where to get that. Do I just go look it up? Well, the electrolysis of water was something that you explored up here. In an electrolysis cell, you do all of this stuff. How much total energy is required to put in the system for the reaction you put in question 1 to proceed? So question 7 is determining the amount of energy that you put into the system to do the electrolysis of water. So for question 17, it's asking you to look at that number and then use that number to find how much is necessary to create 1 mole of hydrogen gas. So the information is just up above, so you know you don't just go look that up somewhere else. 18. There's question about, there were a lot of questions about this one, asking what is this question actually looking for? So this is wanting you to think about the overall system. This overall system is saying that you take water and you split it into hydrogen and oxygen. Then you take that hydrogen and you burn it in oxygen and you get more energy out, is the claim of this device that we're looking at. So what this is doing is saying, take the amount of energy that you get by burning the hydrogen. How much work can be done by 1 mole of combustion of hydrogen gas under standard conditions? You get that number in 16. Over and above the amount of energy that you put in, which you just calculated in 17. So you take the value you got in 16 and subtract the value you got in 17, and it's saying, how much do you have there? And I suspect that, that the confusion that's coming about in this question is that if you do this calculation correctly, you find that 17 is a larger number than 16. And so you're not actually getting any extra energy out. So this question is worded from the perspective of, well, this device claims to give you more energy. So how much more energy do you get? Well, you get a negative number because you actually don't get more energy, you get less energy. It doesn't work. So this question is asking you to step back and think about that process, that aspect. 22. How to approach this question, and I think some confusion about this whole per carbon, per hydrogen perspective. So let's think about this for a moment. This is in the context of, we have octane, we do the combustion reaction, and we just up here for methane determined what the combustion products for carbon and hydrogen are, carbon dioxide and water. And question 22 is asking you to think about why those are the two combustion products for a carbon hydrogen containing fuel. And so it's wanting you to go look at Appendix G of the online textbook, look at the various compounds that have carbon, hydrogen, and oxygen, and look at the numbers that are associated with it. It could be delta G, could be delta H, could be delta S, depending on what you think is the appropriate way to evaluate which of those determine what the combustion products should be. And then it also makes you, says, think about it on a per carbon or per hydrogen basis. So if one of the possible products that you're looking at has 4 carbons in it, then when you burn octane, you make 2 of those. But the carbon dioxide, which should be one of your answers up here in 21, has only 1 carbon in it. So when you burn octane, you get 8 of those molecules of carbon dioxide out. So what really, if you're comparing the C4 kind of compound product to the C1 kind of compound product, you need to keep in mind that you make more of the C1 versions. So what you're trying to figure out is, what is the enthalpy change, if enthalpy is the one you want to look at, or the entropy change, or the Gibbs free energy change, whichever one you're looking at. What is the change of in that thermodynamic property per carbon of the product that you're making? And this is the same thing for hydrogen. What is the energy, entropy, or free energy of the hydrogen product that you're making on a per hydrogen basis? When you look at those numbers that are in that table from that perspective, something should jump off the page at you as being, wow, okay, clearly that's why it's carbon dioxide and water. So that's what this is asking you to look at. Okay. Those are all of the muddiest points that I had gotten on the group activity. Does anybody here on Zoom have any questions on the group activity that you'd like me to go over a bit more? Okay, not hearing or seeing any, I will go on. If some come into the chat, I will come back to it. Okay, so there were some questions about redox and electrochemistry from Piazza. So questions about balancing redox equations that are labeled as being in acidic or basic conditions in the homework of Newton. How does that factor into solving the problem? So this was something I actually specifically went over in this slide on both Monday and Tuesday. We have a procedure that we follow, right? The half reactions, balance everything except O and H, and so on, going all the way down to here, which gives us an answer for balancing it in acidic conditions, which you can tell it's acidic because we have H pluses that are involved. If you are told that the reaction needs to happen under basic conditions, then you have an extra step that you follow up here, where you essentially cancel out the H pluses by adding hydroxides to both sides until all of the H pluses become water molecules. So at that point, then you're able to write an equation for the same redox reaction, but now under basic conditions rather than under acidic conditions. So, so that's what this is looking at here. I'm not going to go through this in incredible detail right here unless people specifically want me to, because I went over it in detail in both of the classes on Monday and Tuesday. Okay, the next question. Still having trouble understanding how standard reduction potentials work, and in particular how it works with the example in class of a galvanic cell. So sure, we can go back and look at that in a little more detail. So let us come here, and so let's look at this reaction right here. So we have set it up so that we have an anode on the left, a cathode on the right. We have on the left-hand side copper turning into copper 2+, copper turning into copper 2+. On the right-hand side, we have silver plus turning into silver. And so the question is, how do we use standard reduction potentials for this? Well, our expression is that we need the standard cell potential of the cathode, standard reduction potential of the cathode minus the standard reduction potential of the anode. So the cathode is the right-hand side. So we want to look at the silver plus going to silver reduction potential. We come over here to our table. Let's see if we can find silver. Silver plus going to silver. So we have a plus 0.8 for our cathode. So I'm going to come back to here, and I'm going to insert a text box so that we have E cathode equals 0.8 volts. Now we look at our, and we're going to subtract the anode standard reduction potential. So here we have copper 2+ and copper. So we come over here. We find copper 2+ and copper. So we have plus 0.34 in this case. We come back up here. E anode equals plus 0.34 volts. So I believe this was, and so what we end up with is our E cell, oops, I need two L's on that, equals E cathode minus E anode equals 0.8 minus 0.34 equals 0.46 volts, which is indeed what we see up here. So the idea, and so here's what I want you to notice as well. So if we look here at the copper reaction, half reaction that we have, notice that this is the reduction half reaction. So this is copper 2+ going to copper and gaining 2 electrons. Up here, we have the opposite thing going on. Copper is turning into copper 2+ and giving up 2 electrons, so it is oxidizing in this case. So that is why what we do is we subtract the reduction potential of the anode, because what's going on is that the anode reaction is oxidation, which is the opposite of the reduction potential that we have. So that is how you use the standard reduction potentials to generate the cell voltage for a given cell. In all of these cases, I should have had a little degree sign on these because we're looking at the standard potentials in this case, where it's happening at 1 molar of everything that's involved. Okay. As always, if people need clarifications on any of these, please type them into the chat and I will address them. Otherwise, I'm just going to keep going on to the next questions that we have. How do concentration cells create voltage? So we went over that a little bit today, and the idea for the concentration cell is that because there is a concentration difference between the two, the half cell potentials of them are different. And so when we use the Nernst equation up here to determine the cell potential, we need to have a Q in here that includes the concentrations on each of the two sides that we're dealing with. And so that is going to, even though E standard cell will be 0 for a concentration cell, because the standard reactions are the same on both sides, just in reverse. Because of Q, because you have different concentrations on the two sides, you end up with an overall cell voltage that is based upon there being that difference in concentrations. Okay. When can a galvanic cell be used in a chemical reaction? So that's literally what the question on Piazza asked. And my problem is I don't understand what the question is asking. The galvanic cell is a redox reaction that is happening. And so is divided into the reduction half on one side and the oxidation half on the other. When can it be used in a chemical reaction? Maybe the question is asking about using it as a synthesis of something. And so perhaps it is trying to get at the idea of having a spontaneous redox reaction and creating a product as a result of that. But I'm not entirely sure. So if anybody has some insight onto what that question is likely trying to drive at, I would love for a clarification on it. When using Q in the Nernst equation, is it always cathode over anode? Well, no, it's always products over reactants. So what you do is you try to write the overall reaction that's happening, and then you use the Q for the overall reaction. Now that is actually a little bit challenging for a concentration cell because you have cancellations that are going on. So it might be actually quite, kind of informative to go through an example of doing that. So let's go to this slide and let's use this nickel example that we have here and figure out how we might use the Nernst equation to solve this problem. So what I would do in this case, so the first thing we need to do is to write the overall reaction. So overall, so we have, I'm going to label this as cathode. So let's make this bigger. Slide this over. We're going to label this as cathode. Then we have really? Anode, and then anode, and then we also need, this needs to be a plus, and then we also need +2 electrons on the right-hand side. Something like that. So I didn't do that very well here. Okay, so that becomes, my mouse is acting up. So that becomes our overall reaction. Okay, so I'll put that up here. Now, notice that there are some things that we can cancel. That can cancel with that, with no problem, because it's the same electrons that are going across. Now, because these are at different concentrations, we have to leave the Ni2 plus in these two places. But when we're looking at an equilibrium constant or a reaction quotient, the solids don't factor in, so we can get rid of those two as well. So what we end up with for our reaction quotient is going to just be the reaction quotient for what we've written here. So in this case, it is going to be Ni2 plus in the anode over the concentration of Ni2 plus in the cathode, and that becomes your Q for the Nernst equation. Now, the reason that I didn't immediately agree, so in this case, it's going to be anode over cathode. But it is always a good idea to write out the reaction like this and then determine the equilibrium constant from the way it's written, so that you can tell which side it's going to be on, because you may end up having the oxidation of the anode being having the ion here and the solid here, if it's going from something that's negatively charged to something that's positively charged. Follow up on the Nernst equation. Newton says that you can take natural log of Q or log Q to derive E cell. How do you know which, when you should use natural log or log? Okay, so let's go to the Nernst equation. That was up here, wasn't it? Nernst equation was here. Okay, so the derivation that we used was natural log. If you use the log base 10 version of it, then you're going to end up with a different constant that is in front. It's going to have an extra, I think, log base 10 of E or something like that that's going to be part of this using the change of base formula. So you may have seen the Nernst equation that it has a number over n, which is already determined at the temperature that, that you're using. That number will be a different number if you are using the log. Personally, I prefer to not use the version that has just the number that's up here, because I like to be able to remember that, you know, if I'm at a different temperature, I need to take that into account. And also remembering that there's this connection between the gas constant and the Faraday constant is useful just from a conceptual standpoint. So I don't like that, that numerical version of the Nernst equation, but some people use it. So, so being exposed to the fact that some people use it is, I think, valuable. All right, you're welcome. So let's see. Okay, so so that was it on redox and electrochemistry in terms of muddiest points. If more questions come up on those topics, feel free to put them in the chat to let me know. Otherwise, I will continue on to some muddiest points, going back to some of last week's stuff on entropy and spontaneity. So why does entropy increase with the number of microstates, and what is the relationship? So that one is the one that is Boltzmann's equation. S equals Boltzmann's constant times the natural log of W, where W is the ways of arranging the system, which is another way of saying the number of microstates in the macro state that you are measuring. So that, that is the connection here. When W goes up, entropy goes up, because natural logarithm is a continuously increasing quantity. So larger W means larger S. How do you calculate microstates, and what impact does that have on entropy? So I am not going to hold you responsible for calculating the number of microstates. We went through the calculations of some quantities of microstates to get across a conceptual idea that the numbers get ridiculously huge, and that the number of microstates in a disordered system is just so stupidly higher than the number of microstates in an ordered system that you will never get a spontaneous process randomly showing up as an ordered system. That was the purpose of it, not that you actually need to be able to do that calculation yourself. And so I am not going to be holding you responsible for doing those kinds of calculations. Okay. How do you calculate delta G when giving the concentrations of the species within the reaction? So that comes back to an equation we used up here to get the Nernst equation, which is right here. So that is comes from this expression. So you can get the delta G standard by looking at tables of thermodynamic quantities, but delta G standard means that you are operating at 1 atmosphere pressure or 1 bar pressure for every gas, and at 1 molar concentration for every solution species. When you're dealing with the actual concentrations you're dealing with, you have to modify it using the reaction quotient, using this expression right here. So, so that is how you use given concentrations to determine a delta G for your specific situation. Under what conditions could a non-spontaneous reaction occur, and has one ever happened before? Okay, so there are, depending on who you ask, there are 2 different ways to answer this question. One answer to it is no. Non-spontaneous means it does not happen, period. End of question. Another way of answering this question that some people use is in order to make a non-spontaneous reaction happen, you need to input work into the system. And so an analogy for that to the idea of the shuffling cards, which we talked about when first introducing the idea, is that spontaneous process is what happens when you randomly select amongst the different microstates by shuffling. Putting work into the system would be I'm taking the cards, looking at their faces, and I'm deliberately putting them into order. So you have to put work in to make that happen. My problem with that explanation is it's not that the explanation is wrong. It's that it's kind of giving a wrong perspective on what spontaneity means. Because I would instead describe it as when you are putting work into a system, you are changing the system in a way that changes what is spontaneous. So you have taken a non-spontaneous reaction and you have made it a spontaneous reaction by changing the conditions of the reaction that you're looking at. So and if you ever go on in chemistry and get to physical chemistry, you'll be able to calculate that. You'll be able to calculate the effect that a particular type of work that you're putting into the system has, and then calculate the delta G for what happens as a result of that. And indeed, you have now taken something that without your perturbation was a positive delta G, and you've made it into a system where it's a negative delta G. So I prefer the first answer, which is that no, non-spontaneous reactions never occur. That's what non-spontaneous means. But you will sometimes hear explanations, even by chemists even, who will say that you can drive a non-spontaneous reaction to happen by applying work to the system. I think that is a misstatement, but it does convey partially the right information, so just be aware of that sort of terminology issue. Okay, why does delta G correlate with spontaneity? And so we talked about why an increase in microstates, an increase in W, correlates with spontaneity. We have exactly the same idea for delta G correlating with spontaneity because the derivation of what we mean by delta G came from us looking at the delta S for the universe being greater than 0. So we split up delta S into delta S of the system and delta S of the surroundings. We turned delta S of the surroundings into minus delta H of the system over T. And then we just multiplied through by negative T to get delta H minus T delta S less than or equal to 0 corresponds to spontaneity. And so that's what we mean by delta G. By delta G. So that's the relationship. Can we use delta G of formation rather than going through delta H, delta S, and then calculating delta G at a given temperature? So let me open something here. I may not have actually kept it. I haven't kept it. Okay. So when you look at Appendix G in the textbook, which has the standard thermodynamic data. So this right here. There is a delta G of formation here. And so the question is asking, can we just use this instead of having to go through calculating delta H of the reaction, delta S of the reaction, and then plugging it into delta G equals delta H minus T delta S? And the answer to that is, if you are confident that you are operating at the temperature that the delta G of formation was measured at, yes, you can do that. In this case, 298 Kelvin. The thing is, though, that in practice, very often you're operating at some temperature that's slightly different from that. You may be operating at body temperature, say 35 degrees C or something like that. And it's relatively okay to assume that the entropies don't change much with temperature. It's relatively okay to assume that the enthalpies of formation don't change much with temperature. But it's not okay to assume that delta G doesn't change with temperature, because it's delta G minus T delta S. There's that T term in it. I mean, yes, the delta H's and the delta S's do change a little bit with temperature, but it's small compared to what delta G does. So personally, I prefer to not use these tabulated delta G's of formation and to use delta H's and the S's and go that way through it, so that I don't accidentally make a mistake of assuming that I'm operating at a temperature that I don't, that is not incorrect in that context. All right, I have gone through the time that I have available. If folks have any clarifying questions on what we've gone over here, I'm happy to stick around a couple more minutes and address those. Otherwise, I will be picking up tomorrow. The first part of tomorrow will be the same starting material that I went over today. That took about half an hour. So if you want to come in tomorrow, come in at about 30 minutes in or something like that. And I will be picking up with more muddiest points at that point and going forward. Or of course, there are the recorded videos. So if folks have some questions now on what we've just gone over, I'm happy to address them. Otherwise, thank you very much. All right, have a good day, everybody.